There is a widely held belief in the field of artificial intelligence that tokenizers are transparent translators. The standard assumption is that a lossless tokenizer loses nothing and adds nothing. It takes your text, converts it to numbers, and when you convert it back, you get the exact same text. It sounds like a trivial observation. It feels like a mathematical certainty that requires no further investigation. However, when we look at the actual mechanics of how large language models process information, this assumption hides a significant complexity. The claim that lossless tokenization is free is not just a matter of theory. It requires rigorous quantification of inference latency and memory overhead. To understand why this matters, we must first look at what a tokenizer actually does. It is the bridge between human language and machine computation. When you type a sentence, the model does not read words. It reads sequences of integers. A lossless tokenizer ensures that this translation is perfectly reversible. If you send a document through a lossless system, you can reconstruct the original document bit for bit. This sounds ideal. In fact, it is essential for applications where data fidelity is paramount. But does it really add nothing? Recent research from Amazon Web Services and their collaborators challenges the simplicity of this view. They introduced a technique called Meta-Tokens. This is a lossless compression method that replaces repeated subsequences in large language model inputs with unique identifiers. Think of it like a dictionary where common phrases are replaced with short codes. In their tests, this approach achieved sequence reductions of 27% and 18% across various tasks. This is analogous to the LZ77 compression algorithm used in file systems for decades. It ensures the transformation is trivially reversible, preserving all semantic and syntactic information without adding extraneous data. The computational implications are profound. Transformer architectures, which power modern large language models, rely on an attention mechanism. This mechanism has a quadratic complexity relative to sequence length. This means that if you have the number of tokens, you do not just have the work. You reduce the computational cost significantly. The AWS study showed that encoding costs were reduced by 47% in some scenarios. This is a massive gain for inference latency. If a model can process fewer tokens, it can generate answers faster and with less energy consumption. However, we must scrutinize the claim that this adds nothing. The AWS authors acknowledge a negligible performance gap compared to uncompressed inputs. They argue this is attributable to current model limitations rather than the method itself. They posit that larger models would eliminate these discrepancies entirely. But there is a catch. The feasibility of lossless tokenization is strictly dependent on vocabulary size relative to corpus entropy. This means a tokenizer cannot be lossless for all inputs without an impractically large vocabulary. If you try to make every unique sequence reversible, your vocabulary explodes. A larger vocabulary increases the memory required to store the model weights. This brings us to the practical bottlenecks. While the theoretical reversibility is sound, the implementation introduces overhead. The process of compressing and decompressing tokens takes time. In a high-stakes production environment, that latency can accumulate. The research indicates that lossless tokenizers often introduce implicit overhead through larger vocabulary sizes or fragmented sequences. This contradicts the intuition that losslessness is a free property. You gain compression efficiency, but you might lose semantic alignment. Consider the trade-off. Current mainstream tokenizers often sacrifice perfect reversibility to achieve better semantic grouping and model convergence. They group words that mean similar things together, even if it means the conversion is not perfectly reversible at the character level. This is why different lossless tokenization strategies yield significant performance variations in downstream tasks. The specific compression method matters more than the lossless property itself. A tokenizer that is mathematically perfect might not be the best for the model's learning process. There are other approaches in the field that do not address these specific theoretical properties. Some discussions focus on hybrid tokenization for specific languages like Turkish, focusing on morphology. Others propose tokenizer-free architectures like T-free architectures like T-free-R, which use sparse representations to bypass tokenization entirely. These are valuable, but they do not answer the question of how to balance efficiency with strict information preservation. The consensus emerging from the relevant literature is that while the observation that lossless tokenizers lose nothing and add nothing appears trivial, the Meta-Tokens study validates its formalization as a critical advancement. This work provides strong empirical support for formalizing lossless tokenization as a practical efficiency tool. It effectively bridges the gap between theoretical reversibility and practical deployment. But we must remain realistic. Lossless tokenization is a necessary but insufficient condition for optimal tokenizers. The primary challenge lies in vocabulary efficiency and semantic alignment rather than just reversibility. If you optimize purely for losslessness, you might end up with a system that is accurate but slow or memory-intensive. In production environments, the decision comes down to the specific constraints of the application. If you are dealing with legal documents, medical records, or code where every character must be preserved, lossless compression is the only choice. The computational savings from reduced sequence length can offset the compression overhead. But for creative writing or general chat, the slight performance gap might not justify the added complexity of maintaining a lossless system. The overhead of managing the compression logic must be weighed against the benefits of shorter inference times. Ultimately, formalizing the trade-off between losslessness and compression efficiency is critical. We cannot rely on the assumption that lossless is free. We must measure the latency and memory overhead when token counts increase with sequence length. Theoretical losslessness often translates to practical bottlenecks if the vocabulary becomes too large or the compression logic too heavy. The Meta-Tokens study shows that we can achieve significant computational savings, reducing encoding costs by nearly half in some cases. But it also highlights that the method itself is not a silver bullet. It requires careful calibration of the vocabulary size and an understanding of the entropy of the data being processed. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.